See, I would either have to resign or make the picture with somebody else.
It's interesting that some people find science so easy and others find it kind of dull and difficult. Especially kids, some of them are just eat it up. And I don't know why it is. It's the same perhaps for all subjects. For instance, lots of people love music and I never could carry a tune. And I lose a great deal of pleasure out of that. And I think people lose a lot of pleasure who find science dull. In the case of science, I think that one of the things that make it very difficult is it takes a lot of imagination. It's very hard to imagine all the crazy things. So now how does it go around a corner, a curve, when the outside wheel has to go further than the inside wheel? And the answer is that the wheels are flanged like this. I mean, not flanged, they're cones. This way. I think of the waves and things that are formed in the water. And when there's lots of people have dived in the pool, there's a very great choppiness of all these waves all over the water. And to think that it's possible, maybe, that in those waves is a clue as to what's happening in the pool. Just like in the swimming pool, except in 3 dimensions instead of the 2 dimensions of the pool. They're going in all directions. And we have an 1/8 of an inch black hole into which these things go. Well, to know a little bit more about it, I'd rather gather a little more of this tiny fraction of the front of light. And so I make a big telescope, which is a kind of funnel. The light that comes over this big area, 200 inches across, is very carefully organized, so it's all concentrated back so it can go through a pupil. Actually, it's better to photograph it, or nowadays to use photocells. They're better instruments. But anyway, the idea of the telescope is to focus the light from a bigger area into a smaller area so that we can see things that are weaker, less light. And in that way, we find there's a very large number of stars in the galaxy. There's so many that if you tried to name them, one a second, naming all the stars in our galaxy, and I mean all the stars in the universe, just this galaxy here, it takes 3,000 years. And yet that's not a very big number. Because if those stars were to drop $1 bill on the Earth during a year, each star dropping $1 bill, they might take care of the deficit, which is suggested for the budget of the United States. So you see what kind of numbers we have to deal with. At any rate, I think that the numbers are a problem in astronomy, the sizes and numbers, and the best thing to do is to relax and enjoy the tininess of us and the enormity of the rest of the universe. Of course, if you're feeling depressed by that, you can always look at it the other way and think of how big you are compared to the atoms and the parts of atoms, and then you're an enormous universe to those atoms, so you can sort of stand in the middle and enjoy everything both ways. But the great part of astronomy is the imagination that's been necessary to guess what kinds of structures, what kinds of things can be happening to produce the light and the effects of the light and so on of the stars that we do see. And I could take an example, an historical example. See it many times in science. By using imagination, you've imagined something which could be, according to all the known knowledge of the laws, and you don't know whether it is yet or not. And that's very interesting. There's a creative imagination, you'd like to call it, not just imagining things that are relatively easy, but something different. And to take an example of a star, as we understand it, the ordinary star like the sun is a great big ball of gas, of hydrogen. It's burning up the hydrogen and so forth, and it's an enormous mass of gas. And it's held together by gravity. You don't have to always understand gravity as curved space. It's good enough for this purpose that force inversely is square of the distance. When things are closer together, the force is stronger. And it pulls everything together. By the way, that's why the world is round, because the globe of Earth is pulled together as much as possible. And if it had a great mountain and an irregularity of a bump or so, it would be pulled in by gravity and it all gets smooth. Rocks aren't strong enough to hold a bump much bigger than a few miles, and Mount Everest is our biggest bump. But on the moon, where the gravity's less, the bumps are higher, the mountains are bigger on the moon. Anyway, to get back to the star, it's all held together by gravity, and it's got a nuclear fuel, which we haven't been talking about, that's burning up the hydrogen and generating energy, which keeps things going. And after a while, it would use the fuel up. And people began to think about what would happen then. And it would be possible to just be gas sort of hanging around, held together by gravity, but quiet. But another possibility was to think, if I push the stuff together closer, the gravity is stronger. Would it hold together? Well, if you push a little bit together, the pressure increases. When you push gas together, there are more atoms and they pound harder, so the pressure's higher, but the gravity's stronger. And it turns out the pressure wins, so it would just come out again. If you push a star in like that, it oscillates. And there are some stars that are oscillating and vibrating and so on, but it turns out if you keep on analyzing it and you push it together very far to the incredible concentration that the whole mass of the sun is down to the size of the Earth or smaller, then it turns out all the nuclear matter, all the nuclei of the atoms are all stuck next to each other tight. The electrons are spaces where the electrons are, and it's all squashed out, and it comes out that when you get to that far, the gravity's strong enough, has overpowered the pressure again. Even though the pressure's got to be enormous, the gravity's got to be even more enormous, and the thing will stay steady at a different size and be nothing but a neutron's nuclear matter, nothing solid nuclear matter. And this is a possibility was worked out by Oppenheimer and Volkoff, and it's called a neutron star. And people waited to see if there were any such neutron stars for years, until recently they found these strange pulsars which emit flashes of radio waves, and later they found light, which can go 30 times a second, for instance, the fastest ones, or maybe 10 times a second, or 1 a second. And at first, that's very mysterious. You're used to stars being big and slow, and how can anything in a star move in a 30th of a second? Well, these things are very small neutron stars, and they're spinning very fast. And there's some, for reasons not yet understood, they're emitting a beam of radio waves, like a searchlight in an airport or something. Those things that go around, boop, boop, boop. So we get the flashes, tick, 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 that fast. To imagine a star, the mass of the sun, doing something, turning so fast as 30 times a second is another one of these big number, hard to conceive imaginary things, okay? And the whole idea that there could be a star of such enormous density that a teaspoon would weigh so much that of the matter that if you put it down on the Earth's surface, it's so heavy it'll just plow right through to the center of the Earth, and things like that. It took a lot of imagination. It comes out of the mathematics and the analysis and all this that help you to make sure you're not making a mistake. And it turns out that such a star was possible, and it turned out later, in fact, they do exist. And that's a good example of how imagination is a useful thing and produces a guessing ahead of time, and how we make advances by using it. Besides just the very difficult thing of imagining all the things that might be up there to explain the things we see. In the case of astronomy, we have a large number of things that we see that we are not yet quite clearly got the imagination to see what it is that's producing them. Quasars are very powerful sources of light and radio waves for very great distances. We can see them because they're so bright. And the exact cause of their sources is only gradually being recently understood in terms of another nutty concept of imagination, the black hole, which is something that comes from following the logic of the gravity theory of Einstein to its ultimate, working out the consequences in crazy circumstances. Suppose you had an amount of matter so great that the gravity force is so much that even light trying to get out falls back. Nothing can go faster than light, and nothing could escape. You couldn't see it. How would you get there? If you had a lot of matter to start with, it could fall together and get into this condition that no longer could the light come out. And so you would have this thing which would continue to attract things to it. Things would go in and nothing would come out. That's called a black hole. And you say, well, how can a black hole, which is absorbing everything, make all this energy that we see? Is that an explanation of the quasar? Actually, it may well be, because if the things are falling in don't go plunk in, but go around, falling in by swirling, then as they fall in and irregularly and so forth, and in the fast motions that it produces, they go down this whirlpool, they generate a lot of energy and friction and so forth, and different kinds of effects, magnetic and electric effects, that could make the jets of matter that come out of the quasar and the radio galaxies in ways that are not really understood. We don't have a real picture of why there are jets of radio waves and so matter emitting radio waves in galaxies. There are galaxies in which great jets have come out of big clouds of matter on each side, which are emitting radio waves. So there's some kind of a source in there that sort of gets wound up and shoots these jets of material out with tremendous energy, and it's guessed that maybe that's a black hole somehow or other. And the somehow or other is the challenge of imagination, which has not yet been answered by anybody with any great confidence. You asked me if an ordinary person, by studying hard, would get to be able to imagine these things like I imagine. Of course, I was an ordinary person who studied hard. There's no miracle people. It just happens they got interested in this thing and they learned all this stuff. They're just people. There's no talent, a special miracle ability to understand quantum mechanics or a miracle ability to imagine electromagnetic fields that comes without practice and reading and learning and study. So if you say you take an ordinary person who's willing to devote a great deal of time and study and work and thinking and mathematics and time, then he's become a scientist. Well, when I'm actually doing my own things and I'm working in the high, the deep and esoteric stuff that I worry about, I don't think I can describe very well what it's like. First of all, it's like asking a centipede which light comes after which. It happens quickly, and I'm not exactly sure what flashes and stuff go in the head. But I know it's a crazy mixture of partially equations, partial solving the equation, then having some sort of picture of what's happening that the equation is saying is happening, but they're not that well separated as the words I'm using. And it's a kind of a nutty thing. It's very hard to describe, and I don't know that it does any good to describe it. And that is something that struck me that's very curious. I suspect that what goes on in every man's head might be very, very different. The actual imagery or semi-imagery which comes. And that when we're talking to each other at these high and complicated levels, and we think we're speaking very well, and we're communicating, but what we're really doing is having some kind of big translation scheme going on for translating what this fellow says into our images. You don't say the two balls, when they come toward each other, turn blue. You know what they do. So the question is whether you could get to know what things do better than we do today. As the generations develop, will they invent ways of teaching and so that the new people will learn tricky ways of looking at things and be so trained, so well trained, that they won't have our troubles with the atom picturing. There's still a school of thought that cannot believe that the atomic behavior is so different than large-scale behavior. I think that's a deep prejudice. It's a prejudice from being so used to large-scale behavior. And they're always seeking waiting for the day that we discover that underneath the quantum mechanics, there's some mundane, ordinary balls hitting or particles moving and so on. I think they're going to be defeated. I think nature's imagination is so much greater than man's, she's never going to let us relax. Nothing's really as it seems. We're used to get, hot and cold, and all that hot and cold is the speeds that the atoms are jiggling. If they jiggle more, it corresponds to hotter, and colder is jiggling less. So if you have a bunch of atoms, a cup of coffee or something sitting on a table, and the atoms are jiggling a great deal in the coffee, and they bounce against the cup, and the cup then gets shaking, and and the atoms in the cup shake, and they bounce against the saucer, and the heat heats the cup and heats everything else. And hot thing spreads its heat into other things by mere contact, because the atoms that are jiggling a lot in the hot thing shake the ones that are jiggling only a little bit in the cold thing, so that the hot heat, we say, goes into the cold thing. It spreads. Going back from carbon and oxygen back to carbon dioxide. And the light and heat that's coming out, that's the light and heat of the sun that went in. So it's sort of stored sun that's coming out when you burn a log. Next question, how is it the sun is so jiggly, so hot? I gotta stop somewhere. I'll leave you something to imagine. Most elastic things like steel springs and so on is nothing but this electrical thing pulling back. You pull the atoms a little bit apart when you bend something, and then they try to come back together again. But rubber bands work on a different principle. There's some long molecules like chains and other little ones that are shaking all the time, that are bombarding them, these chains. And the chains are all kind of kinky and knocked about and shake. When you pull open the rubber band, the strings get straighter. But these strings are being bombarded on the side by these other atoms trying to shorten them by kinking them. So it pulls back. It's trying to pull back, and it's pulling back only because of the heat. So if you heat a rubber band, it'll pull more strongly. For instance, if you hang a weight with a rubber band and put a little match to it, it's kind of fun to watch it rise because it heats more. And there's another thing you can check that this idea is right, that it's heat that drives a rubber band. If you pull the band out, just like when we push the piston in the gas, if you pull the band out, the tightening string hitting those molecules makes them move faster, and so it's warmer. And if you take the band and let it in, then the molecules hitting the strings, which sort of give as the thing hits, they give in to the soft like, and they lose energy when they hit these retiring strings. So it cools. And there is a little way you can do this. You're not very sensitive. It's a small effect. And if you take a fairly wide rubber band and put it between your lips and pull it out, you'll certainly notice it's hotter. And if you then hold it out and let it in, you'll notice it's cooler. At least you'll notice a certain difference in what happens when you expand it, when you contract it. And I've always found rubber bands fascinating, to think that when they're sitting on an old package of papers for a long time, holding those papers together, it's done by a perpetual pounding of the atoms against these chains to hold it, trying to kink them year after year. Well, rubber bands don't last that long, but anyhow, for a long time, trying to hold this whole thing together. The world is a dynamic mess of jiggling things if you look at it right. And if you magnify it, you can hardly see anything anymore because everything is jiggling and they're all in patterns and they're all lots of little balls. And it's lucky that we have such a large-scale view of everything that we can see them as things without having to worry about all these little atoms all the time. But it's nature doing it, and it's just iron and copper. And if you took a big, long loop of copper and had iron at each end and moved a piece of iron here, the other iron moves at the other piece. And if you get it down to the nothing, just moving a piece of iron in a loop of copper and seeing another piece of iron move, you realize what a fantastic mystery nature is. You don't even need the iron. You could, if you at least get this pump primed and started, by jiggling copper strands around fast enough, knotting them and unknotting them and so forth, you can get other copper strands to move at the other end of a long connection. And what is it? It's only copper and motion. And we're so used to circumstances in which these electrical phenomena are all canceled out. Everything's sort of neutral, pushing and pulling. It's really very dull. But nature has these wonderful things, magnetic forces and electrical forces. You comb your hair with your comb and you get some strange condition. So you put it in front of a piece of paper and it lifts up the paper, or the paper jiggles at a distance, far away. And that's, in fact, turns out that that is the thing that's more deeper inside of everything than the things we're used to. We're used to forces that only act directly, right? You push with your finger, it only acts directly. But then you have to imagine what it is that's pushing with the finger. Here's this little finger's made out of little balls and atoms. And it's got another bunch of atoms that I'm pushing. And there's a little space between those atoms. And this pushing is going through that space. And the only thing that happens with the comb and the paper is that circumstances have arisen which make it possible to see that these forces go through a bigger distance than just the short distance between the atoms. What it is we have charges like electrons that are both the same. They repel each other with a force. They're little tiny particles. They're a piece of the atom, and they repel each other with a force which is enormous. It's inversely as the square of the distance, just like gravity is inversely as the square of the distance, but gravity is attractive, and this is repulsive. And for two electrons, the gravity is so weak compared to the electricity. Electricity is so much more enormous than the gravity. I can't express it because I don't know the name of the number. It's 1 with 30 or 8 or 40 zeros after the 1. Bigger is electricity. It's so enormous that if I were all electrons, well, the numbers are too big. So if there's also, however, for electrical things, other kind of charge, positive charges. An example of protons are positive. They're inside the nucleus of the atom, and they attract electrons. Opposite charges attract, and like charges repel. So you have to imagine enormous forces where likes are trying to get away from likes, and unlikes are trying to get near the opposite. What would happen if you had a lot of them? All the likes would collect with unlikes. They attract each other. And they'd get an intimate mixture of pluses and minuses all on top of each other, very close together. You wouldn't have a lot of pluses anywhere because they repel each other. They'll all be compensated by minuses very close. And you get these little knots of plus and minus. The reason that the knots don't get smaller and smaller is because they are particles, and there's quantum mechanical effects that we won't discuss that makes it that you can't get any smaller than a certain size. And so you get these little lumps, which are balls. They're the atoms. The atoms have positive and negative charge, and they're neutralized. They cancel their charge as nearly as they can. And because of this force is so big, it ends up nowhere, with very little left. Because it's so big, it cancels out. There's always so exactly the same pluses and minuses in any normal material. When you comb your hair, it rubs just a little bit extra, or just a few extra minuses, say here, and somewhere else a few extra pluses. But the forces are so big, there's just the extra ones which make a force that we can see that seems to be at a long range. And that we find mysterious, and that we need an explanation for. And we try to find an explanation for it in terms of ideas like the forces that are inside of rubber bands or steel bars or twisted things. We would like to have some kind of puller at a distance because we're used to it, that we don't get any push until we're touching. But the fact is that the reason we don't get any push until we're touching is it's the same force as you see at a long distance, only it's come down to short because the pluses and minuses have canceled out so well that you don't feel anything until it gets very, very close. When it gets close enough, of course, it makes a difference which is plus and which is minus and where they are, and they repel each other. So it's kind of fun to imagine this intimate mixture of highly attractive opposites, which are so strong that they cancel out the effects. And it's only sometimes, when you have an excess of one kind and another, that you get this mysterious electrical force. And how can I explain a mysterious electrical force in any other way? Why should I try to explain it in terms of of something like jelly or other things which are made, and I understand, the other way around in terms of strong long-distance forces which have all canceled out. So it's the electrical forces, in fact, and the magnetic forces, in fact, that we have to accept as the base reality in which we're going to explain all the other things. So again, it turns out it's hard to understand. You have to do a lot of imagining that the real world has as its base a force which acts at a long distance, that we haven't got much experience with that force. We have a peculiar phenomena here and there, But ordinarily, we don't have much experience with that force, is simply because that's what requires explanation. That's what requires imagination. The long-distance force we have no other picture for. And in the example of the generator, for instance, what happens is that the electrons, which are a part of an atom, they're pushed by the motion of the copper wires. And it's wonderful to think that you push a few here, and they get too close together, so they push the others because they repel at a long distance. So it's not just like water, which repels at a short distance, but it's a wonderful fluid which repels at a long distance, and the effects therefore can go very quickly through the wire. If there's a little concentration, you go zing through the wire all over the city at once. And you can use that stuff to make signals. You can push a few electrons here and there by talking in a telephone. At the other end of the line, a long line of copper across the city, the electrons respond because of this very rapid interactions over these long distances to what you're saying in this room. And that they've discovered experimentally the existence of these long forces and these rapid motion actions and so forth was a tremendous thing for human beings. I think that the discovery of electricity and magnetism and the electromagnetic effects, which were finally worked out, the full equations for everything was worked out by Maxwell in 1873, is probably the most fundamental transformation of the most remarkable thing in history, the biggest change in history. I went to a scientific school, MIT, and in fraternity, when you first join, they try to keep you from being, if you think you're smart, from being feeling that you're too smart, by giving you what look like simple questions to try to figure out what actually happens. And it's like training for imagination, you know. It's kind of fun, and I thought I'd tell you some of them that I remember. I learned them. Of course, once you learn them, the next time somebody comes along with this wonderful puzzle, you look at them kind of quietly. You wait 2 or 3 seconds or 5 seconds to show that you were thinking, and then you come up with this answer to astonish your friends. But the fact was, of course, that you were trained by your fraternity brothers as to how to answer these things early on. One of the questions we got was the problem about the mirror. It's an old problem. You look in a mirror, and let's say you part your hair on the right side. Then you look in the mirror, and the image has got its hair part on the left side. So the image is left to right mixed up. It's not top and bottom mixed up, because the top of the head of the image is up there at the top, and the bottom of the feet is at the bottom. And the question is, how does a mirror know to get the left and right mixed up and not the up and down? You get a better idea of the problem if you think of lying down and looking at the mirror. All right, your hair is still on the left side, and now the left and right was the up and down, whereas the up and down, which look okay, was the right and left before. And the mirror somehow figured out what you're going to do when you're looking at it. So to describe in a sort of symmetrical way what a mirror does, that it doesn't look lopsided, that it takes left and mixes it up with right, and it doesn't do the same with up and down. And after a lot of fiddling, we worked out the answer to that one. You see, if you wave this hand, then the hand in the mirror that waves is right opposite it. The hand on the east is the hand on the east, and the hand on the west is the hand on the west, and the head that's up is up, and the feet that are down. Everything's really all right. But what's wrong is if this is north, your nose is to the north of the back of your head, but in the image, the nose is to the south of the back of the head. So what happens really in the image is neither the right nor left mixed up with the top and bottom, but the front and back have been reversed, you see. That which is the nose on the thing is on the wrong side of the head, if you want to. All right? Now, ordinarily, when we think of the image, we think of it as another person. And we think of the normal way that a person would get into that condition over there. It's a psychological thing. We don't think of the idea that the person has been squashed and pushed backwards, forwards with his nose and his head, because that's not what ordinarily happens to people. A person gets to look like he looks in the mirror by walking around and facing you. And because people, when they walk around, don't turn their head for their feet, we leave that part alone. But they get their right and left hands swung about, you see, when they turn around. And so we say that it's left and right interchange. But really, the symmetrical way, it's along the axis of the mirror that things get interchanged. Well, that's kind of an easy one. A harder one, and very entertaining, was what keeps a train on the track? And of course, the answer is, as everyone thinks, the flanges on the wheels. You know, the wheels have some kind of flange on them. But that's not the answer. Those flanges are just safety devices. If the flanges rub against the tracks, you hear a terrible squealing. They're just in case the real mechanism doesn't work. There's another problem with trains that's connected to it. That people all know this about their automobile, that when you go around a corner, the outside wheels have to go further than the inside wheels. And if the wheels were connected on a solid shaft, you couldn't do that. You can't turn the outside wheels further than the inside wheels. And so the shaft is broken in the middle with a gear system which is called a differential. Did you ever see the differential on a railroad train? No, you look at those wheels under a freight car, and there are the two wheels, and there's a solid steel rod going from one wheel to the other. There's nothing. One turns the same as the other. So now how does it go around a corner? A curve when the outside wheel has to go further than the inside wheel? And the answer is that the wheels are flanged like this. I mean, not flanged, they're cones. This way. That is, they're a little fatter, closer to the train, and a little thinner further out. If you look closely, you'll see they got this beveled edge. And it's all very simple. When they go around a curve, they slide out on the track a bit so that this wheel travels on a fatter part, a bigger diameter, and this on a smaller diameter. So when they both turn one turn, this swings further than the other. And that's what keeps it on the track also the same way. Suppose a train's running along on this thing, on the track, and the track's here and here, and the two wheels are exactly balanced, and it's nice and even. Suppose accidentally it gets a bump or something and slides out this way. Then this wheel is on a bigger circumference than this one, but they're on a solid shaft. So when it turns once around, it carries this wheel forward relative to the other and steers the train back on the track. Of course, if it gets too far off on the other side, it goes back and forth, and it stays on the track because the wheels are tapered and the flanges safety. Well, we had a lot of stuff like that we had to learn, to get straightened out before we could become full-fledged members of the fraternity. If I'm sitting next to a swimming pool and somebody dives in, and she's not too pretty, so I can think of something else, I think of the waves and things that are formed in the water. And when there's lots of people have dived in the pool, there's a very great choppiness of all these waves all over the water. And to think that it's possible, maybe, that in those waves is a clue as to what's happening in the pool. That some sort of insect or something with sufficient cleverness could sit in the corner of the pool and just be disturbed by the waves, and by the nature of the irregularities and bumping of the waves, have figured out who jumped in, where and when, and what's happening all over the pool.